Hi everyone, Mr. Lee here. In this video, I'm going to go over projectile motion. So before this video, make sure you watch the vector notation video so that you understand exactly what I'm doing when we're talking about projectile motions. All right, let's begin. So a projectile motion is any object that is in the both x and the y direction, and sometimes the z direction. But that's the 3D stuff, but mostly what you'll see is the x and y direction, and not only that, but the object is usually flying through the air, okay, and thus the name of projectile. All right, now what I'm going to do is I'm going to dissect a simple projectile motion, and why I want to do that is because if you understand how to get the different parts of a projectile motion, you should be able to solve any projectile motion problem. All right, so let's begin. Now, to start off, I'm going to do a simple sketch of a projectile. So I'm going to get a straight edge so that I can draw the ground, which we will call 0 height. Okay, and from there we are going to launch a projectile. We'll just say it's a ball. Okay, we have a ball there, and this ball is going to be launched through the air. Pew! And it lands somewhere far away, and we can call that XF. Okay, so if you remember, I always like to draw out the scenario because I like to draw or write out all of my information on the drawing because there are very specific parts that have specific values and numbers and constants applied to them. All right, so the way that we can imagine projectile motion is that it's an object that is moving both in the x and the y direction simultaneously. So what I mean by that is that if we were to just look at this object in the x direction, all right, we would say that this object is traveling from here, okay, and every second it travels a certain distance. So this is along the x-axis. It travels a certain distance until it stops at xf. Right? That kind of makes sense because that's how it lands at XF. Now, the y direction is a little bit more complicated. So the y direction, you have to use your imagination a little bit. We're not looking at it going from left to right, which is the x direction. We're going to be looking at it as it goes up and down, which is the y direction. So if we were to view, right, if you were to put your camera on the object and just follow it vertically, not side to side, just vertically up and down, we will see something like this. We will see a ball go up, and then it would fall back down. Okay, we wouldn't know how far out it went. We just know that the ball went up and down. And so what projectile motion does is that it combines both of these ideas together. Okay, and so just to give you a sense of what that means, all right, let's break down the important ideas of the x and y motions. So this is what we know. We know that in the x direction, all right, we know that the initial position is usually going to be 0 meters, okay, and the final position, that'll be where it lands, okay, in the horizontal axis, in the x-axis. Sometimes this is called range, all right, or how far out it went. Now this is something cool. Your initial velocity and your final velocity, they are stated to be the same. Okay, and the reason for that is because there is no acceleration along the x-axis. Nothing is pushing it forward when it is in the air. Okay, that's very important. This is one of those highlighted ideas. This is one of those ideas that students miss a lot. Okay, while it is in the air, nothing is pushing it forward. Nothing is making it speed up forward. Okay, in the x direction. So your initial velocity and your final velocity for the x direction is usually the same. Now, just so you know, when we actually do these, I like to put a little x next to those. Okay, so that we know that we're working in the x direction. Okay, and the last thing I want to talk about is time. Now, time doesn't care about the x or the y axis, but from my experience, what I can tell you is that time is found using the y variables first. Okay, so see if you can see how long the object takes to move using the y variables. And here's the reason why. This object, if we were to look at these dots below, okay, that's describing the motion of the object along the x-axis. So The only reason why this object is stopping its motion is because it landed. Okay, and remember, the landing direction is in the y-axis. And so if it never lands, technically it can go on forward for infinity as it keeps on falling. And so that's why time is usually found using the y-axis. So let's break down the y variables. Now, with the y variables, things get a little bit tricky because at different parts of the motion, different things can be found. Okay, usually we say that y initial, okay, is 0 if it's launched from the ground. Now, this is not always the case. Sometimes you'll find an object that is launched at above the ground, and in that case, you'll have to change it. All right, so usually it's at 0 meters if it's launched from the ground, but this is called our height. And same with the landing. Right? Usually it lands at the same level, but just in case it does not, you have to find the height that where it lands. Right? So I'm not going to highlight that because that's not always true. This is just what you have to usually find. Our v initial y, all right, and your v final y, if and only if, okay, so you should write this down. If and only if, I'll write this down. They're the same. If and only if your y initial is equal to your y final, meaning that you land at the same height. So v initial y and v final y, the magnitude is the same. Well, technically vfy should be negative, okay, but the magnitude is the same but negative. I'll write that down, same but negative. All right, and that's because as it is hitting the ground, it is moving downwards. So maybe I should write that down as well. So for vfy, all right, I will say that a lot of students think it is 0, but it is not. Okay, and here is how we know. Okay, so this is a quick little sidetrack. So if vfy is 0, right? So this is my quick little idea. If v of y is 0, then what this means is when an object touches like the floor or the landing of any object, that means it stops. Okay, and this is how we know it's not true. So if we were to get like a paper towel, right, and let's make it like a wet paper towel, right, and then if we were to drop like a golf ball onto the wet paper towel, if this statement were true, as the golf ball hits the wet paper towel, it would just stop there. Okay, now let's think about this. Let's go over the physical possibilities. One, the physical possibility is the paper breaks / rips. So if the paper breaks / rips, then we have a real weird physical anomaly. We would have a golf ball that is just floating mid-air because v sub y says that it's not moving, and that's not the case. Right? Anomaly number 2. If this ball hits the paper towel and the paper towel falls, right? So the towel falls. So if the towel falls because the object hit the paper towel, right, kind of like a collision, and the paper towel falls, then if Vy is 0, then the ball will just float there while the paper towel fell. Once again, a weird anomaly. Now this is what we actually do know to be true. When the golf ball hits the wet paper towel, right, and if it does in fact rip, the ball continues to fall. Okay, the ball continues to fall downwards, and it tells us that upon impact, v sub y is not 0 because it's still moving. Okay, so this is a very important idea and a very important concept. All right, so back to our chart. Our a sub y, if we are on Earth, it is always going to be negative 10 meters per second squared. Sometimes you'll see it as negative 9.81 or negative 9.8 meters per second squared. But for the sake of our math, let's just use negative 10. Right? Now, if you're going to go into higher level physics and you're working on a telescope or whatever, or rocket science, then you should definitely use the correct one. But for our sake, negative 10 works a-okay. And like I described earlier, the time variable is usually found using the y-axis. All right, so with that out of the way, so we did a brief dissection of the motion, and let's do a couple of things on here. So as this object is moving across, I want to point out the peak. Okay, I want to point out the peak right here. So this is peak. Now the peak is very unique. because the total time, so the total time, which we can call t total, okay, that it takes to land, the peak will take exactly half of the total time that it takes to go up. And that should make sense, right? However long it should take to go up should be however long it takes to fall down. So going up, falling down, the time to the peak will be half of the total time altogether. Now this is something unique with these projectile motions. What I'm going to do is I'm going to draw the ball as it is traveling through the first part of this motion here. But I'm going to be drawing the y variables only. Okay, and so let's do that in blue. All right, so when we first launch, this ball, okay, is launched with a great velocity. Okay, so it's going to go up. So this is your Vy. Okay, and as we are rising, this Vy, it starts to shrink. Now, the reason why this Vy is shrinking is because we have acceleration in the opposite direction. All right, so this is a big idea here. So if our Vy is going upwards, we have a acceleration, okay, that is -10, which is going downwards. So for every passing second, this Vy shrinks by a magnitude of 10. So we can see here that according to my rough sketch, with each passing second, it's shrinking by a magnitude of 10. Okay, it's getting smaller and smaller and smaller and smaller until at the peak. Right, now this is one of those very important ideas here. Vy is 0. Okay, it does not go up anymore. It is not moving down. The peak, the Vy will be 0 meters per second. All right, and then once it starts to fall back down, okay, I'm going to try to line it up as it starts to fall back down. And then we have the final one, the velocity will start moving downwards. Okay, and not only that, but it'll start to increase downwards, and that is because our velocity is down. Okay, we got a negative velocity here, and our acceleration is also negative, and so our velocity is increasing in the same direction that it is moving. Okay, compared to over here, our velocity was positive and our acceleration was negative. Right, so it's slowing down as it goes up, but as it's falling, it is speeding up. Okay, so slowing down, and then going downwards, it will be speeding up. All right. Okay, so this is what it looks like in the y-axis. Now, there's something very unique about the x-axis. The x-axis, the velocity, okay, because our acceleration is 0, our horizontal component never changes. Okay, all of these v-axes are the same no matter where you are, and that is because your acceleration along the x-axis is 0. All right, and so what this means here is that you have both the x and the y component. Now, if you remember from the video previous where we talked about vector notation, from there we can decide how fast it's actually moving, and that is the actual velocity of the object. So for example, I'm just going to do it sketching wise. All right, let's take a look at A, we'll take a look at B, we'll take a look at C, which is at the peak, and then we'll take a look at D and E. So that should be a D right there. All right, so at A, all right, at A, when it's first launching, okay, it has a horizontal component. Okay, and it has a great big vertical component, right? Great big vertical component. And so if we were to add these two components together, okay, using the tip to tail method, we will get a velocity like so. And we call that the initial velocity. All right, so this tells us that it is moving up and right. And we can see that with the x and the y components. Now at point B, the reason why I chose point B is because we're getting to the top, but we're not fully there. Okay, we can see that the y component is smaller, but the horizontal component, that's still the same. And so what we can say is that as it is rising to the top, the upward velocity decreases, but the rightward velocity stays the same. And so here we can say it's still going up and to the right, but if I were to really describe it, I would say it's, it's mostly moving to the right. Okay, there's less of that vertical. So this is A, this is B. Now let's take a look at the peak, C. At peak C, we say that there is no vertical component. In fact, it is not moving up or down at all, and in fact, it's just moving forward. So at the peak, the object is moving to the right and to the right only. All right. So, and now we start to fall. So let's take a look at D. So at part D, we see that not only is it moving to the right, and it is also moving downwards. So we can say that at point D, if we were to do the tip to tail method, okay, we would draw a vector like this. So this is saying that it's going both down and to the right. And at point E, we can say point E is equal to point A, except the velocity is down and right instead of up and to the right. Okay, and if I were to do a sketch, it would look just like A. So we got the ball and we have the nice horizontal velocity, but we would draw that nice big vertical velocity as well. And the tip to tail method shows us that a resultant velocity would look like this, and that's what we call v final. Okay, so we can see that as the object is going up, the actual velocity is a tangent line, okay, to that path that we drew. So what this means is, I'll try this in, I'll do this in yellow. All right, that for here, the actual velocity will be tangent to this path. Oh boy, that was ugly. Will be tangent to the path. Okay, right here, it will be tangent to the path at that point right there. Okay, at that point, it's tangent to the path right there. At that point, it will be tangent to the path right there, like so. Tangent to the path. Okay, at the top, it is actually tangent to the path, and here, as it's going down, it's tangent to the path, tangent to the path, tangent to the path, tangent to the path, and at the end, it is still moving down and to the right, so tangent to the path. Okay. Now, I said it was tangent to the path and not actually along the path, because remember, it's a parabolic shape, and so the path is constantly curved. We just want a line that is tangent to that curve. All right, so we went through a lot, and notice we didn't really solve for anything. So the next part of the video, I'm going to actually show you how I would dissect a problem based on what they give us, and how you would actually solve for a different part for projectile motion. All right, I'll see you then. Bye-bye.